Swayam Prabha. Digital India. Educated India.
Welcome back, learners. The video is for the subject of Geography for the course of Bachelor's in Arts with Geography or Bachelor's in Arts with Honours in Geography. The video is for the paper of Climatology Module 2, Solar Radiation, Heat Balance and Temperature. Today we will be starting with the last lecture of this module, Lecture 6, Module 2, which is Inversion of Temperature. The video is being recorded by Dr. Pallavi Upreti.
The course coordinator and presenter for the video is Dr. Pallavi Upreti, affiliated to Department of Geography, Doon University. The academic expert and reviewer for the video is Professor Santosh Verma, Head of the Department, Department of Geography, SDM-PG Government Degree College, Doiwala, Dehradun, affiliated to Shri Dev Suman, Uttarakhand University. The video is produced and presented under the project name DTH Swayam Prabha Channels of MHRD, New Delhi, India. Hello learners, I am Dr. Pallavi Upreti, Assistant Professor in the Department of Geography in Dr. Nityanand Himalayan Research and Study Center, Doon University, Dehradun. In our previous lectures, we have already covered several aspects which are related to temperature. We have covered the horizontal distribution of temperature as well as the vertical distribution of temperature. And in this particular current video, we will be covering one of the important aspects of temperature, which is temperature inversion or inversion of temperature. So let's begin. The main objective of this particular video is to understand what is normal lapse rate and its relation to air temperature. What is inversion of temperature, its meaning and concept. Then we will try to understand what are the different types of inversion. And finally, what is the impact or what are the effects of temperature inversion on atmosphere, on human beings, on other atmospheric phenomena associated with it. Before understanding what temperature inversion is, we must first understand the concept of normal lapse rate and air temperature. As we have discussed so many times in the previous lectures, that we know that our Earth is effectively heated from the outgoing long wave terrestrial radiation, and this outgoing long wave terrestrial radiation evidently heats up the lower layers of the atmosphere which are near to the surface of Earth first, and then slowly and gradually this heat is dissipated to the upper layers of the atmosphere. So in this process, what happens? The lower layers of the atmosphere are heated from below and are warmer as compared to the upper layers of the atmosphere. And as we move up in the troposphere, the temperature gradually decreases with increasing height. So all this phenomena is having particularly in the lower layers of the atmosphere and mainly in the troposphere. This gradual decrease of temperature with increasing height happens at a particular rate. What is the rate? It is of 6.5 degrees Celsius per 1000 meter. So every 1000 meter as we go up in the atmosphere, the temperature decreases at 6.5 degrees Celsius rate every 1000 meters. This particular rate of decrease of temperature with increasing height is called as normal lapse rate. So under normal circumstances, because of this normal lapse rate, what happens? The lower layers of the atmosphere, because they are heated first, they are warmer, and then gradually as we move up, because the air is a poor conductor of heat, it is able to transfer very slowly and gradually and to only few meters or kilometers in the lower layers of the atmosphere only. So the lower layers of the atmosphere closer to the Earth's surface have higher temperatures, and the upper layers of the atmosphere in the troposphere have the lower temperature. So these are the normal conditions which exist in the troposphere, which exist in our atmosphere. Therefore, it is also called as normal lapse rate. So let's understand what normal lapse rate is with this brief illustration here. The normal lapse rate is the decrease of temperature with increasing height. So as you can see here that the temperature here is 30 degrees Celsius, and as we know that the temperature decreases with increasing height. So as we move 1,000 meters up in the troposphere, the temperature decreases at the rate of 6.5 degrees Celsius per 1,000 meters and becomes 23.5 degrees Celsius. And further, as we move up in the troposphere, the temperature keeps on decreasing at this particular rate only. So this decrease of temperature with increasing height is called as normal lapse rate, which happens at the rate of 6.5 degrees Celsius per 1,000 meters. So normal lapse rate is persistent throughout the troposphere till tropopause. So temperature keeps on decreasing with increasing height for the entire length of troposphere till tropopause. So these are the normal conditions, normal temperature conditions which are existing normally in the troposphere. So anything beyond or anything opposite to this is definitely not normal, and therefore we will be now discussing what temperature inversion is. Temperature inversion meaning and concept. Under certain conditions, the normal lapse rate conditions which are existing in the troposphere are inversed. That is, the temperature, instead of decreasing with the increasing height, increases with the increasing height. So the normal lapse rate conditions are reversed. The lower layers becomes cooler as compared to the upper layers, because in temperature inversion, the layers which are below becomes cooler. So your normal lapse rate conditions are not prevailing anymore, and the temperature, instead of decreasing with increasing height as in case of normal lapse rate, tends to increase with increasing height, which is called as temperature inversion. So it is basically the inversion of normal temperature conditions in the troposphere leading to negative lapse rate. Why negative lapse rate? Because the temperature is no more decreasing with increasing height, and instead of decreasing with increasing height, the conditions are reversed and the temperature increases with increasing height, where the warm air lies above the cool air instead of the cool air lying above the warm air as in the normal conditions. So you can better understand with this particular diagram here that this is the condition of normal lapse rate. You can see that the layers which are near to the ground surface soak the outgoing terrestrial radiation first, and then gradually the heat is dissipated to the upper layers of the atmosphere. So this being the warmer and this being the cooler layer. Whereas in temperature inversion conditions, under certain conditions, this particular phenomena is reversed. How reversed? That the lower layers of the atmosphere are no more warmer because of certain conditions which we will be discussing in the coming slides, and the lower layers of the atmosphere becomes cooler and the warm air is tossed up, and it is again followed by the cool layer. So the normal pattern of warmer layer followed by cooler layer followed by much cooler layer is reversed here. So this is what happens in temperature inversions. The normal lapse rate conditions are inversed. There are various types of temperature inversions. First is non-advectional temperature inversion. When the temperature inversion occurs and is associated with stationary air condition, that is, there is no movement of air, the air is stable, there is no horizontal as well as vertical movement of air. So the temperature inversion associated with non-advectional temperature inversion is first the ground temperature inversion, when the temperature inversion occurs near to the surface of Earth because of stable air conditions. And second temperature inversion associated with non-advectional temperature inversion is the upper air inversion, when the temperature inversion occurs in the upper part of the atmosphere, particularly because of the stable air conditions. Besides non-advectional temperature inversion, we have advectional temperature inversions. So temperature inversion can be associated with several weather phenomena and occur due to variety of weather phenomena. It can be non-advectional, it can be advectional. So under advectional, as the name suggests, when the temperature inversion is associated with the horizontal movement of air or due to unstable air conditions, when there is movement of air. Because of movement of air, when there is temperature inversion, it is called as advectional temperature inversion. So first, under that category is frontal temperature inversion, valley temperature inversion, and surface inversion due to horizontal movement of air. All these types of inversion is associated with advectional temperature inversion. Besides advectional and non-advectional temperature inversion, we have a third category also, which is mechanical temperature inversion, which generally occurs at higher heights in the atmosphere due to subsidence of air and turbulence and convective mechanisms. So under this, we have subsidence temperature inversion and turbulence and convective temperature inversion. So we will be discussing all these types of temperature inversions and how they are different from one another and why they develop in the particular conditions they develop and how they lead to temperature inversion. First category under the types of temperature inversion was non-advectional temperature inversion. When under certain atmospheric conditions, the movement of air is hindered, it is slowed down, it is stable, it leads to temperature inversion. The stability of air leads to temperature inversion. Therefore, it is also called as radiational temperature inversion because it occurs near the surface of the earth due to radiation mechanism. It is mainly associated with non-advectional temperature conditions and there is no movement of air. The atmospheric conditions are static and very stable, characterized by no movement of air. A ground inversion develops when air is cooled by coming in contact with a colder surface until it becomes cooler than the overlying atmosphere. So as we know that our earth is heated from below, okay, so when earth is heated from below, earth's atmosphere, the atmosphere which is closest to the surface of earth, it copies its properties, okay, it absorbs the property of the ground surface. So in the non-advectional inversion, what happens when the air lies over the ground surface for a very long time period, the air is very stable, there is no movement of air. What happens, the air absorbs the properties of the colder surface also from below, leading to temperature inversion. So as you can see in the diagram also, normally the above lying air absorbs the property of the ground surface and becomes warmer, but after a point of time, because the air has stayed stable for a very long time period over that ground surface, what happens when the ground becomes cool, okay, when the ground surface becomes much colder, this particular layer also absorbs the cool properties of the ground and becomes cold. So the air layers which are above to this particular lowermost layer becomes warmer as compared to the lowermost layer, and it looks like temperature inversion conditions are developed. So now you have the cold air lying beneath the warm air, leading to temperature inversion. But for this non-advectional inversion to happen, there are specific conditions, especially for the ground surface temperature inversion, there are specific conditions in which this particular phenomena take place. So let's look at the conditions in which the ground surface temperature inversion takes place. First is the long winter nights, so that the loss of heat by the terrestrial radiation from the ground surface during the night may exceed the amount of insolation received from the sun through the incoming shortwave electromagnetic radiation waves, and thus the ground surface becomes too cold, and then the air lying above the ground takes the properties, absorbs the properties of the ground also. Second is the cloudless and clear sky, so that the loss of heat through the terrestrial radiation proceeds more rapidly without any obstruction, and clouds absorbs terrestrial radiation and hence retards loss of heat from the surface of earth. So cloudless sky facilitates the rapid loss of heat. Third one is the presence of dry air near the ground surface, so that it may not absorb much heat radiated from the Earth's surface, as moist air is capable of absorbing much of the radiant heat from the Earth's surface. Next is the very little or no movement of air. In this particular phenomena, why no movement of air? So that there is no transfer and mixing of heat in the lower layers of the atmosphere, and the air is able to completely absorb the properties of the ground surface properly without any movement and mixing. Next is the snow-covered ground surface, leading to maximum reflection of incoming solar radiation. Snow, being the bad conductor of heat, retards the flow of heat from the ground surface lying below the snow layers to the lower atmosphere. So these are the conditions which facilitates the ground surface inversion. So because of these conditions, sometimes fog may also appear in these particular regions when the ground surface cools off too rapidly and the temperature of the surface air drops below its dew point, leading to the formation of fog. And this type of temperature inversion process is commonly seen in the middle latitude, specifically in the winter season, where you have a very stable air, where you have anticyclonic conditions, very stable air, and the ground is able to rapidly cool off and the air is able to absorb the properties of the ground during the winter season, where we have long winter nights. So ground surface temperature inversion takes place in this particular conditions. This type of ground temperature inversion can be seen at many places, especially in the middle latitudes during the long winter nights. As you can also see in this beautiful picture, that it is a morning time, and because of temperature inversion, the lower layers of the atmosphere have become much more cooler. So this is the cooler layer, and this has totally taken the properties of the ground, which has become cold during the night time. So because of these stable conditions, the atmospheric layers have absorbed the properties of the ground surface, and because of which the smoke is also not able to escape, and it has formed the shallow boundary depicting this cool layer, because it is not able to move upward because of the presence of cool dense air, showing a beautiful pattern of temperature inversion. The second type of temperature inversion in non-advection category is upper air temperature inversion, which is also called as thermal upper air inversion, because it happens mainly due to the presence of incoming solar radiations, and this is mainly because of the presence of ozone layer, as it is clearly showing the upper air inversion, that means beyond troposphere. So in stratosphere, because of the presence of ozone layer, the ozone is able to trap the UV radiations, increasing the temperature of this particular layer. So as you know that in the troposphere there is a decreasing trend of temperature, okay, and the decreasing trend of temperature is at 6.5 degree per 1000 meters rate. So till troposphere the temperature decreases with increasing height, but due to the presence of ozone layer in the stratosphere, this particular layer becomes warmer as compared to the lower layer, which is troposphere. So the temperature at the base of stratosphere, or you can say at the uppermost region of the troposphere, is somewhere around -50 to -60. But due to the presence of ozone layer, and ozone absorbs heat in the form of UV radiations, so the temperature increases and becomes somewhere around 0 degrees Celsius. So here what happens, the warmer air is lying above the colder air, leading to temperature inversion conditions. So the upper regions of the troposphere are cooler as compared to the stratosphere, leading to temperature inversion in upper air region. So the presence of ozone layer in the stratosphere between the height of 15 to 35 kilometers is responsible for upper air inversion because it absorbs most of the incoming UV radiations, thus increasing the temperature of this layer, and the temperature of this particular layer becomes much higher than the lower lying layer, which is troposphere, creating the conditions of temperature inversion in the upper air. Besides non-advectional temperature inversion, we have advectional temperature inversion phenomena also around the globe. So the advectional inversion is associated with the movement of air, primarily the horizontal movement of air and the vertical movement of air, non-stationary conditions of air, unstable conditions of air, leading to advectional inversion. First category in advectional inversion is the frontal inversion, which is formed in the temperate regions due to collision of cold and warm air forming fronts. Aggressive cold front invades the area of warm front, leading to the frontal inversion. So as the cold air invades the area of the warm air is forced to toss up, and in this process what happens, the cold air gradually takes over the place of the warm air, completely tossing up the warm air to its upper regions, and finally cold air lies beneath the warm air, leading to the formation of frontal temperature inversion. Second is valley inversion, formed in valley regions due to radiation and vertical movement of air. So as it is clear from the name only that the valley inversion occurs in the mountainous regions due to radiation and vertical movement of air. This is also called as vertical advectional inversion of temperature. So the temperature of the upper parts of the valley in the mountainous area becomes exceedingly low during the winter nights because of rapid radiation. Consequently, the air coming in contact with the cool surface also becomes cool. On the other hand, the temperature of valley floor does not fall considerably because of comparatively low rate of loss of heat through the terrestrial radiation. Thus, the air remains warmer in the valley regions than the air aloft, and hence the warm and light air of the valley floor is pushed upwards because this cool air sinks to the valley floor. In the process, the warmer air of the valley floor is tossed upwards by the descending cold air and heavier air from the upper parts of the valley. So warm air lies above the cold air. So this process leads to the formation of temperature inversion. Cold air, warm air. So cold air coming from the top of the mountain completely invades the valley floor, tossing the warmer air of the valley floor to the upper regions, leading to temperature inversion. The third type of temperature inversion associated with advectional inversion is surface inversion. So this type of inversion takes place due to horizontal movement of air particularly. So either warm air invades the area of cold air, or the cold air invades the area of the warm air, leading to the temperature inversion. So in both the cases, whether warm air becomes aggressive and moves to the area of cold air, in the process the warm air is only tossed up because the cold air is dense, it still wants to sink. So in the process the warm air is tossed up. Secondly is when the cold front become aggressive. So in that process also what happens, that the cold air is aggressively moving to the warmer regions, leading to the rapid tossing up of the warm air to the upper regions, and the whole lower region is covered with the cold air, leading to temperature inversion conditions. So in both the cases, when the warm air becomes aggressive, then also the temperature inversion occurs because the warm air aggressively moves upwards, leading to precipitation. And then when the cool air becomes aggressive and moves to the warm air region, it also becomes aggressive, leading to the formation of fronts and leading to the temperature inversion conditions. So these were the types of advectional inversion. Third type of inversion is mechanical temperature inversion. So such type of inversion is often associated with the upper atmospheric conditions only. The mechanical inversion of temperature is caused at higher heights in the atmosphere due to subsidence of air and turbulence and convective mechanisms in the atmosphere. So first one is subsidence inversion. When in the upper troposphere suddenly widespread layer of air descends, and this descending air is compressed, heated by the resulting increasing atmospheric pressure, is called as subsidence inversion. So this descending air is compressed and warms adiabatically, which is called as subsidence inversion, due to which the upper regions of the atmosphere becomes warmer as compared to the lower regions of the atmosphere, which are much cooler. So because of this adiabatic warming of the air parcel and descending of the air parcel, and in the process its compression and heating, results to the subsidence inversion. Next is the turbulence and convective inversions. Sometimes the warm air is suddenly transported upwards due to the eddies or other sudden phenomena in the atmosphere to the zone of cold air, and the cold air being denser lies under the warm air, leading to the temperature inversion conditions. So these phenomena generally happen in the areas where there is a lot of atmospheric disturbance, lot of atmospheric activity, disturbance happening. So a warm parcel of air is suddenly transported, and because it is warm, it is light, it takes the place of a cool denser air, pushing the cool denser air below it. So in the process, the lower layers of the atmosphere becomes cool as compared to the upper layers of the atmosphere, which becomes warm, and this is called as turbulence and convective inversion. So these are the types of temperature inversion: advectional temperature inversion, non-advectional temperature inversion, and mechanical inversion. Effects of temperature inversion. Now coming to the effects of temperature inversion, although we know that temperature inversion denotes local and temporary atmospheric conditions, but there are several climatic effects of the inversion of temperature which have a great significance to man, atmosphere, economic activities, and several other factors associated with it. So temperature inversion, first of all, determines the precipitation, forms of cloud, and also cause of fog and frost in many areas. So temperature inversion represents a very dynamic atmospheric conditions also, although it is of local nature. It has a profound impact in determining the precipitation, even the types of precipitation, whether it is going to rain or it is going to snow. So all these types and forms of precipitation and even the forms of clouds are determined by the temperature inversion. Secondly, formation of fog is very important phenomena which happens in the temperature inversion conditions. So existence of cold air below the warm air leads to the cooling of warm air from below, creating fog-like conditions. So due to inversion of temperature, air pollutants, so this is very important here, due to the formation of fog and due to the stable conditions in temperature inversion, what happens that the pollutants are also trapped sometimes in below that cold atmospheric layer, and due to which the smoke particles are not able to disperse and escape, leading to the formation of smog, especially in the urban areas during the long winter night, posing serious risk to human health and well-being. So next is formation of frost. When the condensation of warm air occurs due to cooling by air from below, at a temperature below the freezing point, frost is formed. which can potentially damage agriculture crops overnight. So areas of temperature inversion also experience frost, which is very detrimental to the crops which are grown in the region. It covers them with minute ice particles with frost, and which damage the agriculture crops. So economically it can be very harmful for the production of crops, production of fruits in the region. Temperature inversion conditions, formation of fog, formation of frost are also associated with the reduced ability to see, that is reduced visibility. So fog is formed due to the situation wherein the warm air is above and cold air is below. Hence the visibility is reduced, which causes disturbances transport, especially in the valley regions where you have very limited means of transportation. One or two roads are there, so disturbance in transportation is really very problematic in areas which have very limited means and types of transportation. So reduced visibility is another effect of temperature inversion, followed by the another effect, which is the static air, wherein especially in the non-advectional temperature inversion, the movement of air is restricted. There is no movement of air, which leads to atmospheric stability conditions or anticyclonic condition. We will be understanding what anticyclonic conditions are in detail in the coming slides, but just understand that in temperature inversion conditions, due to the atmospheric stability, the anticyclonic conditions are formed. So anticyclonic conditions are formed, cold air takes place the whole region, which is dense, which wants to subside, and because of which there is very less rainfall in the region, leading to dry conditions. So prevailing of dry conditions and very low rainfall is another impact of temperature inversions in the region. Whereas in certain areas where specifically where the areas which are associated with the advectional type of temperature inversion, especially in the frontal regions, the temperature inversion because of the collision of fronts is also associated with fog and high precipitation. But mostly when the temperature inversion is in static conditions, is non-advectional type of temperature inversion, it leads to atmospheric stability and very less rainfall, especially in the middle latitudinal regions of the globe. Coming to the another point, which is the less rainfall. Again, the unstable conditions leads to more rainfall, whereas stable condition, atmospheric conditions, leads to atmospheric stability and associated with less to no rainfall, followed by dry conditions and water crisis, water problems, bad agricultural productivity, less agriculture, and food problems also. The last effect of temperature inversion is associated with extreme weather patterns, extreme weather phenomena like intense thunderstorms, especially in the advectional type of temperature inversion, when the two different types of air masses, big air masses are coming and colliding, having different properties. It may lead to thunderstorms, it may lead to extreme weather patterns and events like thunderstorms and tornadoes, which are associated with inversion of temperature, especially along the regions where the fronts are formed, especially in the areas where the advectional type of temperature inversion is taking place. Where frontal inversion is taking place, the cold aggressive air is trying to invade the warmer regions, and in the process the warm air is getting tossed up to the upper regions, causing sudden atmospheric instability and creating extreme weather phenomena like thunderstorms and cyclones, tornadoes, and extreme weather conditions in the areas. So these are the effects of temperature inversion, although it is of very localized nature and it is a temporary atmospheric phenomena, but it has a widespread impact and widespread significance on several atmospheric and climatic conditions throughout the globe. So summarizing the video, first we have understood what normal lapse rate of temperature is, which exists in the troposphere, where the temperature decreases with increasing height. So these are the normal conditions which are existing in the troposphere. Under certain conditions, this existing normal rate of decrease of temperature with increasing height is reversed, leading to negative lapse rate, wherein the temperature, instead of decreasing with increasing height, tends to increase with increasing height, which is called as temperature inversion. So any condition, any abnormal weather phenomena or atmospheric condition leading to change or inversion of existing normal lapse rate is called as temperature inversion. So temperature inversion is the inversion of normal atmospheric condition or normal lapse rate. It is broadly of types non-advectional, which can be divided into again two: ground inversion and upper air inversion. Second one is advectional temperature inversion, which can be divided into frontal, valley inversion, surface inversion. Third one is the mechanical inversion, which can again be divided into two: subsidence inversion, turbulence and convective inversion. Both of these are associated with the upper air inversions. So these are the types of temperature inversion which we have discussed in this particular video. Besides this, we have also discussed the effects of temperature inversion, which includes that the temperature inversion is a very dynamic atmospheric phenomena, although of regional or local nature. However, it has profound impact on atmosphere, environment, economic, health conditions of human beings, agriculture productivity, and on several atmospheric phenomena and global atmospheric conditions of the world. I hope this video was informative. Thank you for your time.